Good evening, students. So today we are going to learn the Fourier series, examples on Fourier series. In our last lecture, that is before lockdown, we have seen what is meant by Fourier series. Also, we have solved some examples. So some of the remaining examples we try to solve in this video lecture. So the first example is obtain the Fourier series expansion for cos kx in the interval 0 to 2 pi, where k is a fixed constant. So as we have already seen in the definition of the Fourier series, we first write this answer. So we start our solution with the answer, that is the required Fourier series expansion for fx is equal to cos kx is fx is equal to cos kx is equal to a naught by 2 plus summation an cos nx, where n takes values from 1 to infinity, plus summation bn sin nx. Here also n takes values from 1 to infinity, where a naught, an, bn are the constants called as Fourier constants, and we have to find these Fourier constants to find the answer. Now, as we have seen, the value of a naught in the interval 0 to 2 pi is a naught equal to 1 upon pi integral 0 to 2 pi fx dx. So fx is our cos kx. So 1 upon pi integral 0 to 2 pi cos kx. If we cos kx dx, if we evaluate this integral, we will get the value of this integration as sin 2 pi k divided by pi k. Then an, next Fourier constant is an. So as in the definition, we have seen the value of an, the second Fourier constant, is given by an equal to 1 upon pi integral 0 to 2 pi fx into cos nx dx. So that is equal to 1 upon pi integral 0 to 2 pi fx is cos kx. So it becomes cos kx into cos nx dx. So here we have to use the formula from trigonometry first, that is 2 cos alpha cos beta. What is that formula? 2 cos alpha cos beta is nothing but cos of alpha plus beta plus cos of alpha minus beta. So from that formula we are getting an as 1 upon 2 pi to just integral 0 to 2 pi cos of nx plus kx, means n plus k x, plus nx minus kx, means cos of n minus k x. So ultimately our an is 1 upon 2 pi integral 0 to 2 pi cos of n plus k into x plus cos of n minus k into x dx. Now we evaluate this integration. Integration of cos is nothing but sine, and therefore an is equal to 1 upon 2 pi sine of n plus k x divided by n plus k plus sine of n minus k x divided by n minus k, and the limits as we have given 0 to 2 pi. So if we solve this integration by putting the upper limit and lower limits, then we are getting an as k into sine of 2 pi k divided by pi into k square minus n square. Here we are using the formula sine of 2 pi n plus theta is equal to sine theta, and sine of 2 pi n minus theta is equal to minus sine theta, and therefore we have obtained the value of an as k into sine of 2 pi k divided by pi into k square minus n square. The remaining Fourier constant is Bn. So what is Bn? As in the definition, the value of Bn is given as 1 upon pi integral 0 to 2 pi fx into sine nx dx, that is equal to 1 upon pi integral 0 to 2 pi cos kx into sine nx dx. So the only change is we have to multiply fx by sine nx. So exactly on the same way we find the value of this integration. So for that, first use the formula 2 cos alpha sine beta, that is sine of alpha plus beta minus sine of alpha minus beta. So by using that formula, we have Bn is equal to 1 upon 2 pi integral 0 to 2 pi sine of k plus n x minus sine of k minus n x dx. Then we try to evaluate this definite integration. So that is 1 upon 2 pi integration of sine is minus cos, is it? So minus cos of k plus n into x divided by k plus n, then minus minus becomes plus cos of k minus n into x divided by k minus n. The limits are 0 and 2 pi. Now our remaining work is to put the upper limit and the lower limit and take the difference. So by using that, we are getting Bn equal to 1 upon 2 pi minus of cos 2 pi k divided by k plus n plus cos 2 pi k divided by k minus n plus 1 upon k plus n minus 1 upon k minus n. So that is equal to 1 upon 2 pi 2n into cos of 2 pi k divided by k square minus n square minus 2n divided by k square minus n square. Ultimately, it gives Bn equal to n into cos of 2 pi k minus 1 divided by k square minus n square. So using these values of a0, an and bn in our equation 1, that was our answer. So in equation 1 we get fx is equal to cos kx is equal to sine of 2 pi k divided by 2 pi k plus summation n takes values from 1 to infinity k into sine of 2 pi k divided by pi into k square minus n square cos nx plus summation n takes values from 1 to infinity n into cos of 2 pi k minus 1 divided by k square minus n square into sin nx, which is nothing but our required Fourier series. The second problem on this Fourier series expansion is fx. We have given fx is equal to 1 plus 2x by pi, where x lying between minus pi and 0, and fx is equal to 1 minus 2x by pi, where x lying between 0 and pi. So here the interval minus pi is divided into two subintervals as minus pi to 0 and 0 to pi. So as we have seen our first example, we first write the answer exactly on the same way. That is, let the required Fourier series expansion of given function fx is equal to a naught, fx is equal to a naught by 2 plus summation an cos nx, where n takes values from 1 to infinity, plus summation bn sin nx, where n takes values from 1 to infinity, where a naught, an and bn we have to find out as they are Fourier constants. Exactly on the same way, in the last example, we have seen the value of a naught as 1 upon pi. See, here the interval is changed. It is not 0 to 2 pi. Here it is minus pi to pi. Though the interval is changed, the period remains as 2 pi. And see, our a naught we write as 1 upon pi integral minus pi to pi fx dx. But that minus pi to pi is divided into two subintervals with different values of fx. And therefore, we write a naught as a naught equal to 1 upon pi integral minus pi to 0 1 plus 2x by pi dx, because in minus pi to 0 the function is defined as 1 plus 2x by pi, plus 1 upon pi integral 0 to pi 1 minus 2x by pi dx, because in the interval 0 to pi the function is defined as 1 minus 2x by pi. So we try to evaluate this integration. 1 upon pi, integration of 1 is x, integration of 2x by pi is x square by pi, the limits are minus pi 0, plus 1 upon pi, again the same way, x minus x square by pi, the limits are 0 and pi. So for both we are getting the values as 0, and therefore we are getting this a naught equal to 1 upon pi into 0, that is a naught is equal to 0. Then the second Fourier constant we try to find. Here also the value of an, Fourier constant an, is given by 1 upon pi integral minus pi to pi fx into cos nx dx, but that minus pi to pi is divided into two subintervals, that is minus pi to 0 and 0 to pi, and therefore we write an as 1 upon pi integral minus pi to 0 1 plus 2x by pi cos nx dx, plus 1 upon pi integral 0 to pi 1 minus 2x by pi cos nx dx. So we try to evaluate both the integrals, definite integrals, and we are getting this as 1 upon pi 1 plus 2x by pi in one bracket, in second bracket sin nx by n, minus the first bracket 2 by pi, again second bracket minus cos nx by n square minus pi to 0, plus the second integral 1 upon pi, the same way, in the first bracket 1 minus 2x by pi into second bracket sin nx by n, minus first bracket minus 2 by pi into second bracket minus cos nx by n square, and the limits are 0 and pi. See, here we have used the generalized by part rule. I will repeat that rule. The generalized by part rule is like this. Integral uv dx is equal to uv1 minus u dash v2 plus u double dash v3 minus and so on. And this is the most important rule we are using here, and our evaluation becomes simple, and by that rule we are getting an like this. Now the remaining work is to substitute the values of the limit. The values of the limit in the first one 0 and minus pi, and in second one 0 and pi. So in first one, if we put first x is equal to 0, then we are getting this as x is equal to 0 and x is equal to minus pi. Then we are getting this as 1 upon pi into bracket 2 upon n square pi minus 2 times minus 1 raised to n divided by n square pi. And for the second one, that is 0 and pi plus 1 upon pi minus 2 into bracket minus 1 raised to n divided by n square pi plus 2 upon n square pi. And after simplification, finally we are getting an as an equal to 4 times into bracket 1 minus 1 raised to n bracket complete divided by n square pi square. That this is the value of an. Then the remaining Fourier constant is Bn. So Bn is also given as 1 upon pi integral minus pi to pi fx into sin nx dx. But in the intervals we are writing Bn as Bn equal to 1 upon pi integral minus pi to 0 1 plus 2x by pi sin nx dx plus 1 upon pi integral 0 to pi 1 minus 2x by pi sin nx dx. And after evaluation of these limits and substituting the values of the limits exactly as in an, we finally obtain Bn as 0, and therefore our required Fourier series becomes fx is equal to summation n takes values from 1 to infinity 4 times 1 minus 1 raised to n divided by n square pi square cos nx. So that is equal to, if we expand this series by putting n is equal to 1, n is equal to 2, n is equal to 3 and so on, we are getting this as 8 by pi square cos x into bracket cos x by 1 square plus cos 3x by 3 square plus cos 5x by 5 square plus and so on. Why we are getting this like cos x by 1 square plus cos 3x by 3 square? Because the value of 1 minus 1 raised to n is equal to 2 if n is odd, and the value of 1 minus 1 raised to n is equal to 0 if n is even, and therefore cos 2x, cos 4x, cos 6x, these terms will not appear, and therefore our Fourier series becomes fx is equal to 8 upon pi square cos x divided by 1 square plus cos 3x divided by 3 square plus cos 5x divided by 5 square plus and so on. one can extend this question for the deduction and can be asked to show pi square by 8 equal to cos x by 1 square plus cos 3x by 3 square plus cos 5x by 5 square plus and so on. So how this can be obtained? We are getting fx is equal to 8 upon pi square, as we have seen. 8 upon pi square into bracket cos x by 1 square plus cos 3x by 3 square plus cos 5x by 5 square plus and so on. In this, if we put x is equal to 0 and if we use f0 is equal to 1, we are getting the above series as 1 is equal to 8 upon pi square into bracket cos x by 1 square plus cos 3x by 3 square plus cos 5x by 5 square plus and so on. And therefore our deduction is pi square by 8 equal to cos x divided by 1 square plus cos 3x divided by 3 square plus cos 5x divided by 5 square plus and so on. So such type of questions with deductions can be asked for 8 marks. Otherwise, they can be asked for 4 marks. So from the exam point of view, you have to solve such type of examples frequently. Thank you.